Okay, I think we can start. Maybe I'll just quickly introduce. So welcome everyone to the AI-SDM seminar series. This is our second talk, and we do get into technical talks starting now on. So our very first one is given by our co-director, Coty Gonzalez. She's a professor in the social and decision sciences here, of course, works on cognitive models, and she'll tell us about it. So Coty, please take it away.
Thank you. Yes, I'm going to tell you about human-like artificial agents. And we all know this person, Herb Simon, who was one of our own at Carnegie Mellon and who is one of the founders of artificial intelligence. He said that artificial intelligence has two goals. And the first one, AI is directed towards getting computers to be smart and to do smart things so that human beings don't have to do them. And of course, he would be very pleasantly surprised that that is, in fact, very much happening now with machine AI. So machine learning is a form of artificial intelligence that is based on algorithms that are trained on data. So make decisions by using the data instead of using program instructions. And we have seen, especially in the last years, how the advancements of artificial intelligence have really rapidly escalated. And of course, we can see the adaptation of these various algorithms on decision-making. We know that they are playing a big role in our lives, in everyday lives. And now they are becoming extremely advanced. In particular, deep learning is now able to, through multiple iterations, learn very complicated features of various tasks and able to adapt and make decisions in a very interesting and very advanced way. And of course, we see generative AI, which is even able to generate novel content. But this is not what I'm going to be talking about today. The second goal of artificial intelligence is to simulate human beings, and so that we can find out how humans work and perhaps can help them to be a little better in their work. So I am particularly interested in helping people be better at making decisions and at making decisions in highly complex and dynamic tasks, such as disaster situations, global warming, military command and control decision-making. So interestingly, all those type of contexts have similar characteristics. Dynamic decision-making has multiple decisions that you have to make over time. And those decisions are interdependent. They link into each other in ways that generate very distinct paths across time. There is always high uncertainty in these situations, and there is change at different time scales, from the most immediate to the long-term scales. Things are constantly evolving. Many of these problems are about dynamic allocation of resources, and those resources might be time or drones in the case of a disaster, or people. Often there is not enough time in these type of situations to consider all the potential alternatives, and rather we need to move on with what appears to be best at a particular point of time. And obviously, human cognitive abilities are limited. Therefore, our memory and attention plays a big role in how decisions are made in these tasks. So what does machine AI have to do with complex societal dynamic decision problems? Well, a lot. Machine AI has actually been supporting already quite many complex dynamic decision tasks. For example, in the case of disasters, one of the members of our institute is actually using robots and allocating all these limited resources in realistic and quite complex situations of disasters. So these models are aggregating these patterns of data, detecting patterns, be able to forecast, for example, in the case of global warming, and predict events more accurately over time. However, often there is not enough data. And in particular, there is not enough data about human decision-making. So to be able to make high-level decisions, we need to have data about how humans make decisions in those tasks, how they allocate resources with multiple trade-offs. Furthermore, this type of decision-making require really deep understanding of every context and be able to consider multiple and conflicting goals and even ethical and moral trade-offs. Therefore, the ultimate responsibility for this type of decision-making lies with humans, and in my opinion, will always lie in humans or with humans. So our goal has been to improve and speed up human dynamic decision-making. And the approach is by building learning algorithms that can emulate the human cognitive processes and that are capable of making accurate predictions about what humans are gonna do, okay? Thus, we come up with an approach that is a cognitive AI approach. And in this cognitive AI approach, we create cognitively plausible models that can emulate the human decision processes, including the biases and errors that humans make over time. Importantly, these models are based on cognitive theory. What this means is they can explain what humans can do, how humans make decisions, including the predictions of the biases, but in the absence of data. That is, we can simulate the process of decision-making from theory in a particular task and generate decisions, presumably, if the cognitive process is actually accurate, as humans do. So these are also dynamic, actionable models. That is, they are able to learn, they are able to adapt, and adapt to all those changes and make decisions sort of similar like humans do. We can represent experience in these models, and we can make these models synchronize with particular humans, and they can also become collaborators in team tasks. So this is the kind of cognitive AI that we bring to the Institute. And that general goal of understanding human dynamic decision-making translates into two very concrete questions. The first question is, well, to be able to represent these processes computationally, we need to know how humans make decisions. What are the cognitive processes that they use and how they adapt in dynamic tasks? And then we can represent how humans make decisions computationally. So what I'm going to do here is, first, I'm going to give you a very broad overview of decision-making field. And I'm going to tell you about what we know up to this point about dynamic decision-making. And then I'm going to move into representing those processes computationally. So another one of my heroes, Ward Edwards, he recognized the need of dynamic decision-making from very early on. He said that the really applicable kinds of decision theories have to be dynamic, not static. And he predicted that the static decision theories were going to have a limited future. Unfortunately, that hasn't been the case. So this was in 1961, and the majority of the decision theories that we know today are static, not dynamic. And let's start with the classical view of decision-making. So the classical view of decision-making is a linear process Usually, decision makers study one-shot decisions, meaning there is no learning. And the goal is to figure out how, with particular set of alternatives, with particular expectations of certain events and known outcomes, people will choose. And usually we use the concept of expected value, which is a very useful concept to determine what people should do, right? But we know that people don't act according to expected value. And so for a long time, prospect theory has been providing us with more accurate functions about how humans actually make those choices, risky choices in particular. So what they did was essentially to transform the concept of expected value by proposing two different functions of how humans make decisions. And for example, in the case of the probability function, they propose this type of function, meaning that people tend to overweigh low probabilities. And in the case of value, they propose that there is some loss aversion, meaning that people weigh losses more than gains of the same value. This theory is, of course, extremely influential and very useful, and it's still popular to this day. But it is not a learning theory, and it is also limited to gambles, to things that have outcomes and probabilities. So other people said, well, let's expand that idea, and let's really think about how people make decisions in more complex environments. For example, multi-attribute, multi-alternative decision-making. And so comes the heuristic decision-making approach by Gigerenzer and many others, in which they actually propose that very simple heuristics that are cognitively plausible, like in this case, they take the best algorithm, can be better and faster compared to many complicated algorithms. So they actually demonstrated that that is indeed the case. But in this model, there is no learning. Again, there is one-shot decision. Other people, of course.
You have to learn the Q values. You can't use the heuristic until you learn the Q values.
Exactly. So that's exactly what comes after. So other people have said, well, no, people can learn, and people can learn the Q values or the heuristics themselves, when to apply those heuristics over time. So there are other people, and in particular, the SSL model by Rieskam and Autumn has been very influential. And essentially, they are using reinforcement learning as a method to learn the heuristics over time. And then it comes Lee and Glock and others to use Bayesian models as a way to emulate the learning in taking various heuristics. So the idea is that people have some sort of repertoire of heuristics, and the use of those heuristics changes over time. So yeah, individuals can learn, but still it assumes that humans have that repertoire of heuristics that somehow from our head we can pick and use in the right kind of situation. If we go completely in the opposite view of decision-making, there is an area of research that academically might not be very well known, but it is extremely well known in applied areas, in particular in military decision-making, in companies. They all talk about naturalistic decision-making. The main proposer of naturalistic decision-making is Gary Clark. Essentially, the idea is that you study the actual real-world environment by going to the place where the decisions are being made. And you actually do this by field work. So observation, interviews, detecting critical events, doing task analysis. You rely on this observation of experts to make decisions and to figure out how they are making those decisions. And then you are able to determine what is the tacit knowledge, for example, the recognition that they use in making decisions in the real world. So Gary Klein in particular, in his books, he has several books, but one of the books, which is The Sources of Power, describes how he would go into, with the firefighters to find out how they make decisions, and they get to the trucks and they follows them along to figure out how they are making decisions. And then they happen to tell him that they don't make any decisions. He's puzzled. So what do you mean? I just know what to do, was the response, right? So I don't weigh any alternatives. I just know that this is what I have to do in this particular situation. So yes.
Is this connected to imitation learning? That is what machine learning community.
I'm starting to learn more about imitation learning and machine learning. It might be, but at this point, I cannot answer that question. But the naturalistic approach is really, was never put into a computational form. So Gary, who I collaborated with in my early stages of the career, early 2000s, we actually studied military decision-making together. So Gary developed this model that is called recognition prime decision-making. And the idea of this model was that basically people look at a situation and see if that situation is familiar, and then try to recognize several aspects of that situation, mentally simulate potential courses of action, and then finally make a choice. Presumably, all this is happening in an instant. The problem, of course, is that this model is a picture, and it's an interesting process that makes sense, but it's not implemented computationally. So we get to dynamic decision-making. It was very clear to me that to make progress in understanding dynamic decision-making, it was not going to be possible by me going in a truck with the firefighters. I was not going to be able to do that. So how can I study dynamic situations without having to go to the field? Well, Brent Bremer, other people like Joachim Funke, Alex Waring in Australia, large European tendency, worked on the process of dynamic decision-making using microworlds. So the idea is that we can study decision-making in the laboratory by essentially constraining real-world situations into games that we call microworlds. Other people call management flight simulators, etc. So, but the idea is that you can represent those situations in the real world, the cognitive part at least, in a computer simulation in a game, and then be able to run experiments so that you can control what are you studying and be able to find out how people make those choices. There is particularly an emphasis on learning. So the idea is, of course, that we are not going to study experts, because usually experts are not going to come and play our games in the laboratory, right? But we are actually going to study how people acquire that expertise. So how they go from being a novice to being an expert. So we are interested in the process of learning. So throughout the 27 years that I've been here or something like that, we have constructed a lot of microworlds in my laboratory. And actually some of them are commercial video games. Some of them are actually out of the store. Others actually have been developed here in the Entertainment Technology Center, and they vary in different contexts and different kind of tasks. I'm going to summarize some of the findings that we've had up to at least 2017, but some of them are obviously still applicable now. So some of the findings that we have from experiments. So when I came to this area, the view was very pessimistic about what humans are able to do. Essentially, the idea is that people are very poor at making dynamic decisions, even when you provide them with full feedback, unlimited time, high incentives, and extensive practice, they make poor choices. And in particular, humans have a difficulty handling long time delays. This was the main theme of research back in the 90s and early 2000s. But that was very interesting, at least to me, and there was some sort of problem with this assertion of pessimistic view of human decisions, because I could see the experts that are able to make pretty accurate decisions in extremely complex tasks. So how can we reconcile such a thing? So I realized that the reconciliation is exactly in the learning process. So those experts were able to become expert in some way, right? By making multiple repeated decisions. So then we started to investigate in a more positive way, how can we help people to make better decisions? So one of the ideas was that we need the headroom or the cognitive space to be able to learn and to be able to make those better decisions over time. So we demonstrated in various experiments that if you allow that space for people to learn, they are going to be able to do better once they are in a more constrained situation. We also have found out that heterogeneity of experiences is extremely important for learning and adaptation. So when you have a large diversity of experience, your chances of adapting to novel situations are higher. We have also found out and made a direct connection between our ability to pattern match, that is to find similarities, and making better decisions in these dynamic tasks. We measure pattern matching with the Raven Progressive Matrices test. And finally, we found that some types of feedback, in particular feed forward, that involves, for example, observing expert behavior, will help in future dynamic tasks, even when you remove the feedback. So these are some of the findings that we get up to this point. But essentially, in conclusion of all these years of research, were sort of put together into this paper in 2003. So two elements are essential. One is the recognition process. So recognition means determining similarities between a situation and past experience, and identify whether a situation is typical or not. Memory is essential. So with practicing a task, we acquire context-specific knowledge that is allowing us to make better choices over time. And contrary to the heuristic approach, we actually found that people move away from applying these generic heuristics as they acquire more experience. Why? Well, because they can make use of the very contextualized knowledge that they are acquiring in the task, and they acquire these cause and effect relationships. What do I do and what do I get out of the decision I make? So now let me move to the second part, which might be, yes.
Actually, Coty, sorry, I think you have explained this, but I want to make sure I understand it before you move forward. When you talk about dynamic decision making, I guess there are two components I've seen even in like two slides ago when you were talking about it. One is making decisions under dynamic situations when you have high workload, time pressure, and all that.
Mm-hmm.
And the other aspect is the dynamics of the decision itself, as in the people might change opinions as you go and as more evidence is presented. So are you talking about both?
They go together.
Okay.
So I can see that if we change the dynamics of a situation, we can still have dynamic cognition or dynamic of, my preferences over time, even in less dynamic situations, but they go together, right? So how how do we make decisions is totally, in my opinion, context dependent and environment dependent. And we, through the years, have come up with a generalized theory of decision making, and we have demonstrated how that process is more generic. But still, you have to figure out what is the context in which that process is going to be applied. So I think they go hand by hand. So let me go to the second part then, and our approach is that of cognitive architectures. Again, in the tradition of Carnegie Mellon, Alan Newell many years ago defined the concept of cognitive architectures, meaning constructing a single computational system that can reproduce all aspects of human behavior. That was his vision. The idea is that we could represent all the cognitive steps necessary for performing a task and be able to explain the components of the mind that would work together in an integrated form. That vision was amazing, but I do think that it's extremely complex. And through the years, it has proven to be very complex. ACTAR, I believe, is really the architecture that represents that vision. And ACTAR, again, was developed here at Carnegie Mellon by John Anderson and highly supported by Christian Levier, my long-term collaborator. So in my personal view of this architecture, what I prefer to do is look at a simplified version of this architecture and end up looking at the architecture only from the perspective of decision-making and only from the perspective of experiential decision-making, which is what I'm interested in. So I look at it as having two dimensions, the way information is represented, and what are the statistical and mathematical mechanisms that are used to manipulate those types of information. Based on this theory, on this cognitive architecture, we developed a theory of decision-making that is called instance-based learning theory. And it's essentially a cognitive algorithm of how people make decisions in dynamic tasks. So this figure here represents the process. As you can see, it's a process with several loops. So it's not a linear process. But the idea is that decisions are made by recognizing similar situations in decisions made in the past. So recognition is the first step in this algorithm. The second step is evaluating the actions according to the utility of past decisions, which are stored in memory. The third step, is executing a choice, and we can execute the choice once we have mentally explored other potential actions and be able to hold that action that we believe is the best possible action of what we have evaluated, and then be able to execute the one that is best up to that point and modify the environment accordingly. And then at some point we get some feedback from the environment, and we can then update or reevaluate the utility of the decisions that we have in memory. So this theory assumes that we have a representation of every decision we make over time. So the idea is that decisions are stored over time, and they consist of three parts: features of the environment, an action to be taken, and an outcome or a utility. For each potential action, in this case, two actions, what we assume is that those instances are blended according to similarity to create what we call an expected utility or blended value. And then we select the option that has the highest blended value, and we store an instance in memory. At some point when we have feedback from the environment, this expected utility or blended value is updated with the actual outcome observed. Okay, so that's essentially how the algorithm works. And this is the mathematics behind the algorithm, yes.
Why is it called blended value?
It's a mix or a, the idea is you don't use only one past instance to make a decision, but rather a combination of instances that are brought together based on the similarity. The name came from Christian Levier, and he did his dissertation here at Carnegie Mellon in mathematics learning, and he used that term before. So I think it makes sense to call it that way too. All right, so this is the mathematics behind that model. And the first and most important equation is, of course, activation. So activation is a cognitive concept. And the idea is that we have all these memories in our mind, and they have a value, the value of activation that will help us remember and retrieve that information from memory. This activation equation has three components, actually has four, but we only use three. So the first component defines the frequency and recency of experiences. The second component is the one that defines the similarity of the features across experiences. And the last one is a noise component that simply provides variability in human behavior. So these are the three elements. All we did was to grab it from Akhtar as it is, but we discretize time. So Akhtar usually uses continuous time. This value is then used to determine the probability of retrieval of a particular instance from memory. And then it is combining what we call the blended value, which, as you can see, is a form of expected value, but with a cognitive probability that is derived from all these factors and the outcome or expected utility. And then we select the maximum of those blended values. There was a question here.
Yeah, I was just wondering that, can you assume that what happens if you are faced with a new situation that never happened before in your knowledge base?
Yeah, great question. So the assumption in this theory, so the assumption in this theory is that we cannot calculate the expected utility based on memory, and we use a heuristic in those cases, or we use also something that we call pre-populated instance. So you can represent past experience on instances, so we can insert those in our model, or we can use a simple heuristic. And the idea is that over time, the pre-populated instances are going to decay because they are never experienced, and the heuristics are also going to go away because you are acquiring more information in the particular task.
By heuristics, do you mean that the heuristic for what action I should take under such scenario?
Correct. And it can be a very generic heuristic, like take the best, or whatever heuristic, or random, right? It can be any heuristic. The idea is that you need something precisely to act on situations that are not similar in your memory, and there is, you don't pass the threshold of the similarity.
But you still don't guarantee what will happen under that pre-assumption.
No, that exactly. So that is only a way to evaluate, to do this judgment process. So that is only a way to evaluate the potential utility of that decision. Okay, so that's not a decision yet, right? So it's just a way to do the judgment. But then, you can go ahead and evaluate as many alternatives as you have time for, right? And then make a choice. And it might be that that ended up being the best, the one that you created through the heuristic. And that's okay. It's already in an instance, and it will be reused later on as part of your memory. Okay.
So
Yes.
Coty, I also wanted to mention that there's this concept of experience replay that's used in reinforcement learning. I don't know if you're familiar with that. The idea is similar, that you want to store a memory of experiences you have had in the past, and you make decisions based on like what's currently, you're learning as you're taking actions. But
Mhm.
then if you're not sure, you sort of refer back to this memory, and
Right.
which sounds similar. and I
Definitely,
think
there
it's-
is a lot of connections
Yeah.
between this and reinforcement learning. Of course, Barto and what's the other name? The other author.
Oh, certain, yeah.
Yes,
I think that's-
that book came out in the early 90s. This theory is from 2003. So we're working, I guess, on similar ideas from very different perspectives. And this is obviously a cognitive theory, which reinforcement learning is not. But there are many connections, yes. Okay, so I'm going to try to move a little faster from this point on. All the time in the past, most of the time, what we have been doing is try to demonstrate that this theory is a general theory of decision making. And we have been doing that by making a human play these various tasks and making a model from simulation and from the theory, play these various tasks, and then compare the performance of these two. And since we have cognitive processes in this IBL model, we can compare decision by decision, action by action, human by human in the particular task, right? So what I'm going to do now is show you a bunch of snippets of examples of human likeness of IBL agents. And of course, there's lots of stuff behind each of these, but the whole point of this is to show you these examples of how we compare human performance and IBL performance. Importantly, all the data that you are going to see in the various examples comes from simulation. That is, we never fit data in all these examples I'm going to show, okay? So the first one is a binary choice task, but it's not a simple binary choice task. It's actually a learning task. So participants actually need to make choice between two options that have probabilities and outcomes associated to them. And they are going to go over time trying to learn which of the two options is going to provide them the best outcome from experience. And this graph shows 60 different problems with different probabilities and outcomes. And this is the proportion of risky choice. And we have the cognitive model, which is the black line, and the human data, which is the dotted line. So, out of the box, the model is able to emulate the average performance of human data in these 60 different problems in this particular task. Of course, we want to figure out more the dynamic environments. So in this case, there are 4 examples of binary choice, but we are going to have changing probabilities of the best outcome over time in different directions. So we see the predictions of the IBL model in the black line and the observed human data in the dotted line. And we see how the IBL model and the human data follows one-on-one. Yes.
The human here is group data.
The observed is human data.
Is
Yes.
it many humans average?
Many humans average. Yeah, all these are average, and I'm going to come back to that. Correct. The next snippet is about prisoner's dilemma. So we were interested in figuring out whether this model can make predictions about learning to cooperate over time from experience in diets that are playing the prisoner's dilemma under different information conditions. So if we don't provide any information about the other person and the actions of the other person, or when we actually provide the actions and the outcomes of the other person in this task. So we observe from both human data and model, in this case, the model is the lighter line, that more cooperation emerges, the more information we provide about the other person. And furthermore, the model out of the box is able to predict some of these trends. Furthermore, it is also able to predict the sequential dependencies over time. So for example, predict the defect action after the two defected, or the cooperate action after the two cooperated before. So these are the dynamics of the sequential dependencies of the actions over time. And then we wanted to see whether this can escalate to networks. So are we able to predict the performance in different configurations of networks? So we use a taxonomy of two-player tasks from Valier, and we took a particular dimension from that taxonomy. And these are, we run the model in all the parts of the taxonomy, but this particular dimension came out to be interesting. What this dimension says is that when the two players' outcomes and actions are independent, people are going to figure out what the best action is pretty quickly, the best common action pretty quickly. And actually faster, the more connections there are in the network. However, when there is interdependence, okay, when my outcomes depend on the other person's actions, people have difficulty learning what is the best common action. And in fact, the more connected the network is, the more difficulty they have. So these are pure predictions from the model. And we thought, oh, this is interesting. Does it really happen? Let's try to run this model and these predictions of the model with empirical data. Of course, we cannot run thousands of teams. So we run 24, 25, and 26 groups, which are connected in this form. And these are the results from the human experiment. So we can see that the model was pretty accurate in making those predictions. This one is more complicated. It's about learning to detect phishing emails. Phishing emails obviously have a lot of attributes. So this is not a simple binary choice task. So there are lots of attributes in an email. This particular data set presented real and simulated emails, and they asked participants to evaluate the email based on this scale from definitely not suspicious to definitely suspicious. We took that data set and we run our model in the same task. And this figure presents the human data, and this is the model data. And as you can see, it's very similar. This is another complicated task, and this is a lot of the applications that we have in my lab are on cybersecurity. So we see in this case, the role of the player / IBL model is to defend a network against two different type of red agents or attackers. Beeline attacker knows exactly what the path of attack is going to be in the network to reach the final target. The meander attacker strategy just walks around the network trying to find the target. This is the interface of the micro world we use to run human data. And also the model was running the same task. Again, the human or the IBL model played the role of the defender. Here we observe the IBL model playing against the beeline and against the meander attackers. And these predictions were actually published and submitted before we run the study. And here is the results from the empirical study. As you can see, again, we cannot run human participants for 2,000 episodes, so we have to run them for a small number of episodes. But as you can see, the results of the empirical study are qualitatively similar to those of the IBL model. So let me summarize. So there is evidence of human likeness of the IBL algorithm. However, and I take this very seriously, there is a lot of work to do, especially to formalize the cognitive processes, some of them more than others, but also to generate metrics of human likeness. So as you have seen here, and Roderick pointed out, all these are average, comparisons. So we do have individual data, but can the model actually predict the variability of the human behavior and can predict the dynamics over time? I would say yes, but to a certain extent. So we need, again, more accurate metrics of human likeness. I think we need to put absolutely high priority to empirical work, in particular empirical work on learning in dynamic tasks and on identifying the cognitive process of recognition, exploration, stopping rules, and feedback processes and how those are represented. How can we represent those computationally? We also must demonstrate the usefulness of this cognitive AI in improving and speeding up the human decision-making. And just to conclude, I'm going to give you 3 examples in which we are using these models. So the first example is to use, to generate synthetic data. Given the fact that machine learning models are so data hungry and the fact that data is so scarce, we can produce human data by running our IBL model multiple times. We have demonstrated this process in this particular paper, which is a cybersecurity task. Another way to use our models is to actually personalize recommendations, or in this case is the defense strategies in a cybersecurity task. So by emulating the human attacker with our models, we are able to provide predictions of what the attacker is about to do for the defense side. And the defense side then is able to adapt the allocation of resources in a particular test bed. This has been demonstrated in all these papers. Finally, the model can also be a collaborator with humans. And that's things that we are currently doing in the lab by asking an AI, an IBL model, to collaborate with a human in a particular defense task in this scenario. So I just want to thank everybody that made it to this presentation here and people online, but in particular to all the people in my lab, 4 of them here. Thank you very much, because they are the ones that do the work, it's not me. And if you are interested in learning to construct IBL models, you can go to our website and download our architecture, and there is a tutorial, etc., and you can work on that. Thank you.